Hello, fams. In this very lesson, you're going to be looking at the sixth worked example on circular motion. Now, we've been on circular motion for quite some time, and we've taken about five major examples, on circular motion. Today, we are looking at the very sixth one. So, before we solve this very question, if you think, you could, give it a try, I'll give you some time to do that very quickly. Welcome back, guys. Now, were you able to solve this very question? Now, if you cannot solve this very question, now join me as to do justice to this very question together. Now, let's see what we have right on the board. A mass, 5 kg, hangs at the end of a pendulum of length 3 meters, which is released at an angle of 40 degrees to the vertical. Find the tension in the pendulum at this angle to the nearest whole number. Now, don't forget we are dealing with what I can call the canonical pendulum. In our previous set of lessons, we derived various formulas of various stuffs under, uniform circular, motion. So if you have not seen those very lessons, you find it very hard to understand what we're about to take. So today, I will not be deriving those formulas again. I'll just have a quick recap through the various formulas we derived. So quickly, now, what formulas are we going to use to solve this very question? A mass 5 kg, that's the pendulum bob. I can say that's a pendulum bob, hangs on the end of a pendulum of length 3 meters. So we have the length. The length is 3 meters and it's being released at an angle of 40 degrees. The angle is, as a theta, 40 degrees. Now don't forget 40 degrees of the vertical. So we are asked to get the tension, the force of tension. That's what we are looking for. But what formula or formulas are we going to use? So quickly, I'll just have a recap through the canonical pendulum. So we have something like this. We have something like this. That's a canonical pendulum. Now, this pendulum at the point was like this. You have the bulb, but it was raised, look at it, it was released at an angle of 40 degrees. So we have stuff like this, 40 degrees to the vertical. Now, when this happens, this is what happens at the end of the day, it starts rotating. It rotates like this. So we have stuff like, we have something, here's a radius, there's a tension. Don't forget that there's a mass. The mass there is 5 kg. So the mass here, the force of weight, downward weight, which is mass times gravity. So there's a weight down like this acting, while there's a tension in this place fighting back in the other, in the other direction or opposite direction. So quickly, I'm not deriving the formula again. I just want to run through it. There's a radius. And don't forget, for the fact that we have a tension like this, the tension is going to be resolved into 2 dimensions. There'll be tension along x-axis and tension along y-axis. Whenever we have stuff like this, force of tension, this theta. So you have force of tension along, x, like this, a force of tension along y. So if this is what we have, what's going to be the force of tension along s? The force of tension along s is force of tension sine theta. Don't forget opposite, hypotenuse, adjacent. That's what we have. So that's that. Then force of tension along y is force of tension cos theta, adjacent by hypotenuse. Now we know that. Now, by the time we do the summation of forces along the y-axis, don't forget we have a force, we have the downward weight, which is mass and gravity, and we have the force of tension along the y-axis, which is acting in the opposite direction, as you can see. Look at the direction of it like this. So now by the time they come together, for the fact that there is no movement along the y-axis, it means the resolution of the forces along the y-axis is going to be 0 Newton. So what it means is that the force of tension along the y-axis is going to be equal to mass times gravity. Very important. And don't forget the force of tension we're talking about here is Ft cos theta equals to mass times gravity. Now, when you look at the resolution of forces along the x-axis, now there is no other force along the x-axis other than the force of tension along the very x-axis. And it's what brings about the movement, the circular movement. In short, the force of tension along the x-axis is equal to what we call the centripetal force, which is mass times velocity squared over radius. So the force of tension along the x-axis, just trying to have a quick recap through it, is going to be force of, centripetal force, angular force, which is mv squared over radius. This is what we have, apart from this set of formulas. Now, by the time you equate this, by the time you bring this together, Ft, which is Ft along S, which is Ft sin theta over Ft cos theta, will give us no sin. That this takes out this sin theta over cos theta will give us tan theta. So it's also the same thing as mv squared over r divided by mg. So we're going to end up having tan theta, which is equals to, if you look at this, mv squared over r divided by mg, that'll be tan theta, which is equal to v squared over gr. So by the time we equate them, we end up having v squared equals to gr tan theta. So I'm quickly trying to, derive the formulas we need. Now, this is another formula here. Now, when you look at this, this is a radius, this is a length, this is the length of this very, pendulum cord or thread, whatever it is. Now, when you look at this angle faces here, upward, opposite, overward, hypotenuse. So that means radius is equal to L sine theta. So we could have this v squared equals to g L sine theta, which is radius, sine theta, then tan theta. This is what we have. So yeah, all the formulas derived on the canonical pendulum. So if you want a kind of deeper understanding or analysis, I'd love you to go through those very lessons. So now it's high time we solve this. Now, how do we get the tension in the pendulum? For us to get the tension in the pendulum, don't forget there's a tension here. So for us to get the tension in the pendulum, we could use the force of tension along x-axis, or we could also use the force of tension along the y-axis. So if we choose to use the force of tension along the x-axis, we could do it in 2 dimensions, or 2 ways. If you choose to use the force of tension along the x-axis, that means you're going to use this force of tension, which is mv squared over radius. Now, that first of all, it means you have to get the velocity. Now, how do you get the velocity? There's a velocity here. V squared equals to gl sine theta, or that is tan theta, or v squared equals to gr tan theta. Now, we are not given the radius. We can easily get the radius. The radius is L sine theta. So let's use this. This is the best we could use. So we want to get the velocity. So what's going to be the velocity? Velocity is equals to the square root of gravity. What's gravity? Gravity is 10 meters per second squared. That's well known. 10 times, what's the length? The length is 3 meters. The length is in the right unit, 3 meters. Then sine, what's the angle? Sine 40 degrees times tan 40 degrees. So velocity is equals to, quickly, we're going to use our calculator to solve this. So velocity, which is gravity times length. The length is 3 times sine theta times tan theta. So let's quickly do that with our calculator. Square root of 10 times 3 times sine 40, then times tan 40 degrees, will give us 4. So the velocity is 4 meters per second. This velocity we have here. So this very pendulum moved, with a speed of 4 meters per second. This velocity is a linear velocity. Now, after we've gotten this velocity, now quickly, don't forget we are using this. We want to use this first. So what's going to be the first force of tension along the x-axis? Force of tension along the x-axis is mass and velocity squared over radius. Now let's move on. Force of tension along the x-axis is equals to the mass. What's the mass? The mass we're talking about here is 5 kilogram. The mass is in its right unit. Times velocity raised by 2, v raised by 2 over the radius. What's the radius? The radius was not given, but we can easily get the radius. The radius is length times sine theta. What's the length? 3 times sine 40 degrees. So let's quickly use our calculator also to make this very quick. What do we have? We have 5 times 4 raised by 2 is 16, divided by 3 times sine 40. That will give us 41.48. 41.48 is about, let's say 41.485. 485. So let's say that's 41.5. Let me use that. It's 41.5. Now, this is the force of tension along the x-axis, 41.5 Newton. Now, after we've gotten the force of tension along the x-axis, it's high time we solved for the force of tension itself. Now, look at this formula. Force of tension is force of tension sine theta. So you're just going to easily get the very angle we are talking about. So force of tension along x-axis is force of tension sine theta. So how do we do that quickly? We've gotten the force of tension along the x-axis, which is 41.5. So we're just going to equate it. So this 41.5 Newton, because of the force of tension we are looking for. Sine, what's the angle? The angle is 40 degrees, sine 40 degrees. So it's a divisible side, both sides by sine 40. What do we have? So the real force of tension in this very string is 41.5 divided by sine 40. Let's do that very quickly. 41.5 divided by sine 40 degrees. What do we have? 64.56. We have 64.56. 64 0.56. Now don't forget, to the nearest whole number is equals to 65 Newton. This is the force of tension in this very pendulum cord. As simple as ABC. Very, very easy. If you don't want to use this approach, we could use another approach quickly. I will show you how we could use the approach of force of tension along wire. This is a shorter one. Just to just lead us directly to our answer. It's quite very short and very, very quick and effective. So let's use that. Let's use the other approach. So we're going to use the other approach right now. So let's see how we could use the force of tension along the y-axis to get the force of tension in the very cord. So how do we do this? This is how we do it. Let's see. Now, as you can see, force of tension along the y-axis is mass times gravity. Force of tension along the y-axis is mass times gravity. So the force of tension along the y-axis is, what's the mass? The mass you're talking about there is 5 kg. That's the mass. 5 kg. So 5 kg times gravity is 10. So 5 kg times 10 meter per second squared is 50 Newton. That's a beautiful one. So the force of tension, along the y-axis is 50 Newton. Now, if the force of tension along the y-axis is 50 Newton, now how do we get the force of tension itself? Don't forget that the force of tension is force of tension cos the angle. So what's that going to be then? Force of tension along the y-axis is force of tension times the cos of the angle we're talking about. So what's the force of tension along y-axis? It is 50 Newton equals to the force of tension times cos of the angle. What's the angle? 40 degrees. So you're going to divide all through by cos 40 degrees to get our absolute force of tension. So force of tension now is 50 divided by cos 40. Let's solve together. 50 divided by cos 40 degrees. What do we have there? We have 65.27. We have 65.27. That's 27 Newton. Now to the nearest whole number is 65 Newton. As simple as ABC. So this method is very short. It's a very direct method. The first one is, the first approach is analytical approach. That's using the one along the x-axis. So this how to tackle this very question is very, very easy and very interesting. So we're going to be drawing the curtain on this very lesson. So if you found this lesson very helpful, I would love you to, follow me at Facebook. Follow me on Facebook at Revelation Hub, and also subscribe to this very channel at EduMosaic. Please share this lesson also with others. See you in the next lesson. Thanks.